Okay, so then let's consider the second problem. That is, we have the system of structure that's composed of two links. Okay, it's composed of two 10 kilogram bars. Okay, which are pin connected. We would like to find the first question is if the bar is released from race when theta is equal to 60 degrees and the applied force P is become 0. Okay. And we would like to determine angular velocity of bar A, B, and BC at the instant of theta is become 0. So then this is Linda is going to go to the floor here. Okay, move that. Okay. This is we just would like to find the angular velocity omega of AB and BC. Okay, and the second one. Okay, the second one is if horizontal force P is equal to 30 Newton, and this applied to the roller C, we would like to determine angle theta for equilibrium. That is, you will see that if we release it without the force P, the link should be goes down. Okay, but if we maintain the equilibrium with the force P of 30 Newton, so what is the equilibrium configuration for that? We will apply the principle of virtual work for solve this. Okay, so we starting with the first problem, the first question. This is we may starting with draw the free body diagram, set up the coordinate system, and set up the positive sign convention. So for this case, we found that point A is the fixed point, and it should be the reference. We set up the axis here. That is x and y here. It's axis x and y. So then it means that x is to the right is positive and y is upward. It's a positive one. Okay, and we set the line of axis x as the data. Okay, so at the looking line, and this is the for the first picture is it show the first position. That is you will see that the center of gravity of two logs is above the datum that we already set. And for the second position, that's after it's released, okay, it's may going down and it's going up until the theta is become 0. Okay, so then the line of two links become along the datum. Okay, so then we draw this picture, and after that we may consider the point C at this position become the IC. IC is the instantaneous point of zero velocity. So then it means that at this instant, okay, point C has 0 velocity, and we can set up point C as the center of rotation to predict the velocity of point B and the middle point of member BC. Okay, as shown in this picture. Okay, according to this, we may consider the kinematics first. Let's for the case that when theta is equal to 0 degree, okay, that is at the final position, and we found that IC is located at point C. So then it means that VB2 is equal to omega BC. Okay, RB sub IC now. Okay, and if we consider VB2, that is this point. Okay, we can determine VB2 also from the member AB instead. That is VB2, that is at the same point. If we consider the member AB, that is rotation about fixed axis, that is the fixed axis is become at point A. Okay, and then we found that omega AB2 times RB sub A, it should be equal to VB2 also. So according to this equation, we can we know that it is a same point, that is a VB2, both are VB2. So then it means that the magnitude of omega BC, the angular velocity of the member AB and member BC should be, the magnitude should be the same. Okay, but the direction is maybe not the same. Okay, for BC, for member BC, omega should be counterclockwise, but for member AB, omega BC should be clockwise. Okay, and according to this, we found out the magnitude is equivalent. Okay, and then we move to determine velocity of point G at this point. This is the velocity of point G of the member BC. It is equal to omega BC 2 times RG sub IC. As RG sub IC is become 1.5. Okay, and then it has we can determine velocity like this. Okay, and then after that we form the kinetic energy. Okay, this is we applying the principle of conservation of energy, because this system is the conservative system. It's composed of just only the conservative force, that are the gravity force only. Okay, so for the kinetic energy, okay, at the first position, it is start from rest, so then it means that kinetic energy at the first position is become 0. So we consider the kinetic energy at the final position, as is when theta is become 0. We found that we have two members. The first one, this is the member AB. Member AB is the rotation about a fixed axis, and it's rotated about point A. So then it has actually one term. Kinetic energy is come from the rotation. That is half IA omega AB squared. And for member BC, it's a general plane motion. So it has both translation and rotation. So then we have two terms. Okay. After that, we substitute each value into this equation, and then we found out the kinetic energy at the final position is become 30 omega BC squared. Okay. Okay. And remind yourself that omega AB here, actually the omega AB, the magnitude of this is equal to omega BC. So then that's why we can solve this term, solve the kinetic energy at the final position. It's in terms of omega BC, just in terms of omega BC. And for potential energy at the final position, it becomes 0 because it's along the datum. And for the first position, this is equal to mgy1. Okay, y1 is equal to 1.5 sine 60 degree. Okay, and this we have to remember. Okay, so then we can determine this is equal to 254.87 Joule. Okay, according to this, we form the conservation of energy. That is the energy at the first position equal to energy at the final position. The energy is composed of potential energy and kinetic energy for each position. And after we substitute to this, we can solve for omega BC first, that is equal to 2.91 radian/sec. And for omega AB, because the magnitude is are the same, so then it should be the same, that is 2.91 radian/sec. But the direction is maybe not. Okay, that is complete this problem. Okay, and then we move to for the static case. That is we found out for this case we will apply the principle of virtual work. The principle of virtual work is applied for finding the equilibrium position of the rigid link. Okay, that is for this case we set up the coordinate at the fixed point. That is how we set up. Point A is a fixed point, so then we set up the coordinate x to the right as a positive 1, and y is upward as a positive 1. So according to this, It means that when we measure point C, this is the point C here, and this is point B. Okay, this is point B, right? Okay, so then we can find XC. XC is a measure from the reference to point C. Okay, and SC is measured from the reference to point. Actually, I mean, change the notation. This is a H, maybe HB instead. Okay, oh, sorry, HG, that's all right. Okay, not point B, we consider point G, okay, because the gravity is located here. Okay, so then this is maybe HG here. That is the 1.5 sine theta. 1.5 is come from half, okay, a half of 3 meters. And after we have HG, that is upward as positive, and XC is to the right at the positive, according to the positive sign convention here. Okay, and then we take the first derivative. That's it. Actually, in the word of the in mechanics, we may call it like this is the take variation of HG. That is same like the take the derivative to that. Okay, we have H equal to 1.5 sine theta. So then we can find the variation of HG by take the first derivative to the right hand side. That is become 1.5 cosine theta and variation of theta. Okay, and in the same manner for XC, we have the variation of XC is equal to minus 6 sine theta, variation of theta. So from this equation, we found out, okay, if the negative signs, it means that if theta is increased, so then it means that if theta is positive, so del XC, so then the change in value of XC is tend to decrease. Okay, if theta is increased, del XC is tend to decrease. Okay, so then del XC is become negative. Okay, in the same manner for del H, you see that if del theta is positive, so then it means that if theta is increased, okay, so then del H is positive also. So then it means that when theta is increased, H is increased also. Okay. So according to this, we apply the principle of virtual world. The principle of virtual world states that the principle of virtual world states that the system of the rigid body is in equilibrium when the virtual work done of the system is 0. Okay, so then for this case, we form the virtual work done, that is variation U is equal to 0. Okay, the virtual work done variation U is composed of two terms of force. That is we have the gravity force mg, and for the work done from mg, it is negative because we set up upward as a positive, right? So then mg is the opposite to the variation hg that we set up goes up as a positive. So then we form that it should be the work done, it should be negative. Okay, and for the force P also, we set up to the right as a positive. Okay, but force P to the left, so then the force P is opposite to the displacement delta, virtual displacement delta XC. So then it's produce the negative work done. So we're starting with this equation first. And after that, we set up delta U equal to 0 for equilibrium. Okay. And we will find out, we have this equation now. And del XC is the negative sign here. Okay. And we have to note that delta theta is not equal to 0. Okay, for this equation. If delta theta is become 0, so then this equation, you will got the trivial solution. That is no meaning for this equation. Because if delta theta is 0, so the left hand side is 0, the right hand side is 0 also. So then it's correct, but actually it's we got nothing from this case, because if we set up delta theta equal to 0, so then it's no meaning, right? Okay, but for this case, because we assume that delta theta is not equal to 0. So according to this equation, you will find out we have minus 2mg 1.5 cosine theta, okay, plus p times 6 sine theta, okay, and both multiplied with delta theta equal to 0, right? And when we set up this is not equal to 0, so then it means that this term in the bracket, it should be equal to 0 instead. So according to this, so then it means that we can form this equation. That is, this equation can use to determine for theta, that is tan theta is become this value. And after that, we can determine for theta, that is equal to 58.55 degrees. Okay, let's complete this problem.